Okay, so let's get started.
Okay. Good day, everyone. I would like to welcome you all to the APRU Sustainable Waste Management Global Lecture Series. I am Kumuduni Palansurya, a PhD scholar at Korea University, and I'm serving as the Secretary of APRU SWM program. Before starting today's event, I would like to invite Dr. Yuan to provide the technical instruction for the webinar logistic for the attendees. Dr. Yuan. Dr. Yuan, we cannot hear you.
Okay, sorry. Hello, everyone. Thank you for being with us in the second session of Global Lecture Series. As Kumduni mentioned, today I'm going to collaborate with the webinar logistics. Here are some recommendations to consider during this event. This is the webinar mode, so you can listen and see the panelists, and also it's possible to interact through the following tools. We have enabled two chat, so you can ask questions to our speaker or panelists at any time through Q&A chat, and also on the general chat, you could leave comments or share important information. If you are interested to talk and ask a question, please raise your hand and I will unmute you so you can interact directly with the panelists. As it is a global event, we kindly ask you to use the English name all the time. Besides, if you have any problem and issue during the event, please feel free to send a chat to me and I will try to help you. Thank you.
Thank you, Dr. Yuan. APRU SWM Global Lecture Series is organized by the APRU SWM program, where Professor Young-Sik Ok at Korea University serves as the director of the program. This program is co-directed by Professor William Mitch at Stanford University and Professor David Wardle at Nanyang Technological University in Singapore. The second lecture of APRU SWM Global Lecture Series will be delivered by Professor Ann Hyun Park from Columbia University in the city of New York in the USA. At the end of her presentation, there will be a Q&A session. And so I encourage all the attendees to participate the event actively and come up with your questions for the discussions. So now I would like to invite Professor Ok to give a warm welcome to the attendees.
Hey, hello everyone. I'm Young-Sik Ok, who is director of APRU Sustainable Waste Management Program and chair of this session. So APRU has a membership of president of 56 leading universities from the Pacific Rim. This includes 2 million students, over 200,000 academic staff. So APRU Sustainable Waste Management Global Lecture Series is basically designed to provide a sound foundation in basic principle and unifying research across ecology to conservation, environmental health to waste management, while paying more attention to ESG, environmental, social, and governance, and global sustainability. Particularly, some selected topic will be discussed through APRU Sustainable Waste Management Global Lecture Series, focusing on E-Pillar at ESG. So the key topic of APRU Global Lecture Series are conservation, ecology, environmental health, sustainable waste management, carbon neutral, global sustainability life cycle assessment, and so on. So as you know, we have consistently tried to carry out a variety of programs designed to accelerate academic activity and international cooperation. So this series is a part of a regular range of events offered by our APRU program and is designed to offer the audience an inside view of cutting-edge research topic from leading university in global. So I believe the participant will be able to learn from and interact with world-renowned scientists around the world through this lecture series, and I hope that this event will become a valuable opportunity to extend and share friendship among those who participate in the webinar. Thank you very much.
Thank you, Professor Ok. So today, Professor Xianang Wen from National University of Singapore is joining as a panelist for this session. So I would like to welcome Professor Wang for the session and my sincere appreciation for joining with us today. Since this lecture is part of the Seoul Climate Initiative program, we would like to share a video from Chris Timmermans, who is the Secretary General of APRU. This video features an introduction to APRU and why this webinar is part of this important initiative. Dr. Yuan.
So as a resident in the western suburbs of Sydney, one of the most prominent impacts of climate change would have to be the increasing intensity and frequency of heat waves. And in particular, I realized that when you live in energy inefficient or poorly designed buildings, it's very difficult to stay cool and safe during these sweltering periods. And that's translated to me into an awareness of how the impacts of climate change are spatially differentiated, disproportionately impacting marginalized, disadvantaged communities or people in peripheral spaces.
So I might be studying in Japan now, but I'm actually coming from France, from the southern region, the French Alps. In recent years, the winters have gotten a lot warmer. We're getting a lot less snowfall. Biodiversity in the mountain has become a lot less diverse. This is a threat for my community because in my home, tourism is the main source of revenue and the main economy.
The effects of climate change in the country are manifested and felt in our food supply and in the varying weather in the country. For example, extreme drought or extreme flooding brought about by climate change can gravely affect the productivity of our agriculture and fisheries sector. More so, global warming also intensified the calamities that we face. For example, super typhoon, which isn't something that we would consider as normal 10 years ago. But because of the continuous warming of the ocean, we are now unfortunately expecting it to hit us at least once a year.
This is urgent. There is no time to lose. We have to make sure that this planet is safe for humans to live. For everyone, not just the rich. I'm Chris Timmermans from APRU. We are a network of 57 universities around the Pacific Ocean, Asia, North and South America, Australia and New Zealand. Many of you are joining Solve Climate by 2030. We can do this and we can do much more. Together we can make a difference. Let's do it.
I actually believe that everyone can do a little bit of something to fight climate change.
We've seen how the climate crisis is mobilizing an entire new generation of active performative citizens, with students in schools and universities acting in solidarity and participating in protests, demanding change.
Also, we must demand accountability from big-scale polluters such as the big companies who dominate the market and the government who leads the country, because as long as these two refuse to act upon it and neglect the reality of climate change, all our individual efforts such as tree planting or shifting to a zero waste and green lifestyle will all be disregarded, because fighting a big and complex issue such as climate change requires collective action.
Now we will move to the second lecture of Global Lecture Series. It's a great honor for me to introduce our speaker, who is Professor An-Hyun Park from Columbia University in the city of New York. Before starting the lecture, I would like to give a brief introduction about Professor Park. Professor Park is the Landfest Institute Professor of Climate Change at Columbia University and is also the Director of the Landfest Center for Sustainable Energy where her research focuses on sustainable energy and material conversion pathways in emphasis on integrated carbon capture, utilization, and storage technologies addressing climate change. Professor Park has received numerous honors and distinction throughout her career as a researcher, including the USC3E Research Award, PSRI Leadership Award at American Institute of Chemical Engineers, and Chemical Engineering, American Chemical Society Energy and Fuels Division Emerging Research Award, American Chemical Society WCC Rising Star Award, and the National Science Foundation Career Award. A graduate of the University of British Columbia, Professor Park received a Bachelor of Applied Science with distinction and Master of Applied Sciences, both in chemical and biological engineering. She received a PhD degree in chemical biomolecular engineering from the Ohio State University. So Professor Park, over to you.
Thank you. It's great to visit you guys virtually. So I wanted to bring Columbia University in New York City a little bit virtually, although I think outside it's quite dark because it's a little after 8 p.m. But the beauty of a virtual world is that we can visit anyone, anytime. So I'm really happy to visit, and I really enjoyed watching the video, and I think that links to my talk quite nicely. So let me share my slide. Can you see it well?
Yes,
Great.
yes, we can.
So I don't think I need to talk about the climate change. We just heard that, and I'm sure that all the attendees here feel passionate about climate change mitigation, adaptation, and all the issues related to climate change. And so the title of my talk is Towards Sustainable Energy and Materials. That's my research field, but I'm addressing this issue of sustainability in the energy and materials sector by doing carbon capture, utilization, and storage, which is quite linked to climate change mitigation. I'm not sure how many of you are aware that during the COP21 in Paris, there was a mission innovation movement. There was a number of different types of mission innovation discussions happen at the time. There was one with the billionaires like Bill Gates talked about how to do this quickly. But at the same time, there was a mission innovation discussion among different ministries of different countries, including South Korea, and many countries just talked about during this video. So 23 countries and EU, which means the entire world, got together and talked about how to address climate change issues. So if you look at these buckets, what they said was, let's look at what is the science and technology we really need to advance. And at the time, they came up with 7 buckets first. So here from smart grid all the way to affordable heating and cooling of the buildings. And a year later, they added hydrogen. So now there are 8 buckets. But what they were doing was a little bit different than what the video just talked about, right? The video said climate change is crisis. We need to solve it by 2030, which is true. There are a lot of areas we need to address by 2030, and we should do it. We should have solved this issue yesterday. We're way too late. We should do this. But at the same time, this mission innovation discussion was very interesting. And I think if some of you are graduate students, this is important for you. Because what they said was our climate change mitigation technologies or research is not going to be only for 2030 or 2040 or 2050. We project the climate change impact even 2100, right? You see all these predictions and all that. So when you think about it as engineers per se, I think some of you are, do we have technology which we're going to deploy in 2100 today? The answer is no, right? Because normally from your idea all the way to commercialization, most of the technologies takes less than 20 years. So the fact that all the ideas we have today will be deployed within 20 years, hopefully sooner than later, that 2100-year technologies, we don't have it yet. That kind of makes you think, right? Which means that we'll advance science and technology so much by 2100, we just don't know what we're going to have then. So what they were saying at the Mission Innovation with all these countries came together, entire world, saying that not only we need to do deployment of the technology we already have, but we also need to think about how to advance fundamental science and technology and engineering for 2100 and beyond. What does mean is, although climate change really requires us, for example, short, very fast diet, but you almost have to change your lifestyle for the better world. And that's very important because this is not a short bridge, it'll be a long bridge, generations to come. And as you can see in these buckets are not independent from each other. They're quite linked to each other. So if you have a lot of renewable electricity, you can do a lot better, maybe sustainable biofuels, or make better hydrogen, or we can even do carbon management. So looking at these really give you idea that what we really need to invest for the future for research and development in these areas. But today, I'd like to tell you more about the third bucket, carbon capture, utilization, and storage, which I usually do work on. So with all the discussion, I was one of the co-chairs for led this mission innovation workshop on carbon capture, utilization, and storage. We call it CCUS. And that report was published in 2018. You can free to download from Department of Energy. This gives you not the roadmap, but vision statement on what science and technology we should really focus on, what are the fundamental challenges and questions we should ask ourselves for next decades to come. And I think there are other topics you can also find in the workshop reports. So let's go back to carbon capture, because if you want to do CCUS, you have to capture carbon first from somewhere. And if you are trying to find the carbon or capture it, of course, you're going to go to point source. That's the first thing you will do, because if you know that there's some emission of some kind and there's a chimney, of course, that's where you want to tackle it first. And when you look at the carbon dioxide, without going into too much of chemistry side of it, carbon dioxide is very similar to sulfur dioxide. Sulfur dioxide, we studied a lot in decades ago because acid rain, but it's a lot more reactive than carbon dioxide. So at the end of the day, in order to address carbon dioxide, it's acidic gas, so you need a base. So if you're doing chemically, for example, there are many different chemicals you can choose from to react this CO2 to capture in the stable form. So if you look at this plot from Department of Energy in the United States, this is ready for demonstration versus cost reduction benefit. So obviously they think the chemical looping or membrane technologies are a little more far into the future compared to amine-based solvent, which is basic liquid solvent. This is something we can do today. The technology, like amine-based solvent, is a weak base. So what happens in the first reactor in green color, it will react with or in contact with gas and liquid phase, and then capture CO2 and absorb it into liquid phase. Then the gas now depleted in CO2 will be released into the stack. At the same time, the CO2 loaded liquid now go into the second reactor. And that's the really important part. Because if you're using this CO2 capture liquid solvent only once and throw it away, that doesn't make sense. The reason is any chemicals or materials you see around or you use have an environmental footprint, including carbon footprint. So that if you're just capturing CO2 and then throw it away, that doesn't make sense in terms of economics as well as environmental footprint. So which means you have to do catch and release. And catch part is energy downhill. So it works well. And especially if your binding energy is large enough. But then now you have to pay energy in to release CO2 so that that material can go back and capture more CO2 for the second round and next round. So that this red color reactor is a solvent regenerator. So when you talk about CO2 capture, that's where you put energy in. And a lot of times the energy, what we are doing right now, is coming from power plant itself, which means that either you have to burn more natural gas or coal, or your power plant capacity will go down by 1/3. which is a big challenge. So people are really concerned about, yeah, we know how to do chemistry really well and capture CO2 and release CO2 for compression and sequestration and put it into pipeline. But at the same time, this solvent regeneration reactor will cost you a lot of energy. But because we know a lot about this technology, we actually did a lot of demonstration in the world. In US, unfortunately, we only had one, started 2000, I think December 2016. I took this particular photo in Houston, Texas. It's called Petronova project. It operated for a couple of years and seems to be okay. We didn't get as much data as we hoped, but now it has been stopped. And that's because the low cost of the crude oil right now, and I can discuss it later on. The operation itself, I don't think is a big challenge. We learned quite a bit about what will be the bottleneck for commercialization of this technology. But one of the things we have to go back here is that this particular amine-based materials cannot be used as a pure form. So if you're using 100% pure this liquid solvent, it's very corrosive, very hard to work with. So what you do is like MEA, monoethanolamine, you have to dilute it in water. So maximum concentration, usually amine in water-based liquid solvent is about 30 weight percent. So if you have 30 weight percent, means that you have a 70 to 85% of a liquid going between these two reactors is water. And we love water because so many reasons, but one of the things is it has high heat capacity. Sometimes it works well for us, sometimes it doesn't. In this particular case, it doesn't work well for us because you have to heat it up so high, about 120 to 140 degrees C quickly, and then you have to cool it down to 40 to 60 degrees C quickly. And all these energy penalty makes CO2 capture very expensive. So there were a series of research being going on how to do better heat integration between these capture and solvent regeneration reactors. But at the same time, people start looking at, well, we love amine capturing CO2, but then we don't particularly like to have all that water running around. So can we make materials which is either water lean or waterless? So this been kind of, I would say, second generation CO2 capture materials been really studied around the world. And some include, these include ionic liquids, cobalt, and something called NOMS, which was developed by Lyndon Archer at Cornell University and my group at Columbia. I'm not going to go through chemistry of ionic liquids and cobalt. But one thing we really like about ionic liquid is that there's so many combinations of cation and anion, so chemical tunability is amazing. At the same time, you can heat up this ionic liquid to hundreds degrees C and still has no fumes. It's almost like a zero vapor pressure, which makes it very nice for applications as such as the CO2 capture when we do a lot of temperature swing technologies processes. So NOMS material, we call it, is a nanoparticle organic hybrid materials. We make these by tethering polymer onto nanoparticles. By doing so, we do right grafting density and optimize the length of these polymers. We can keep this material not as solid. Although we start with a solid nanoparticle, the final material is a liquid-like material. It looks kind of like honey. And because of that, this polymer chain should be flexible. So when we make this as a waterless, by removing all the water, we hypothesize that these polymer chains will be stretched out from each other so that not only enthalpy will work for us having amine groups, but entropy will work for us to capture CO2. So initial materials we made was some of these. We made them without any amine functional groups just to see that by grafting these polymers right grafting density and size, can we really improve the thermal stability? And if you look at the bottom left, compared to untethered polymer, by tethering polymer, either ionic or covalent bond, making NOMS, we were able to improve the thermal stability by 100+ degrees C. This is really great, but one cycle not going to cut it, as I told you, right? We need to do many, many cycles. So the initial cost of your solvent should go into the noise of the operating cost of your plant. So if you look at the picture on the bottom right, we have NOMS compared with the polymer we started with. When the polymer, which is untethered, degrades 80% over 100 cycles, NOMS sustain pretty well. This was the first sign we thought that, well, this is great. We might be able to use this for multiple cycles of gas separation, such as carbon capture. But then one of the things was, going back to my hypothesis, can we really structure the polymer which is tethered so that we can gain the entropy effect, not only enthalpy effect? So we looked at the 2D ROSY NMR without going into too much detail here. Left and right is, left is a pure polymer which is untethered, and then tethered polymer in NOMS is on the right-hand side. Only thing you need to see in this NMR data is there a lot of interaction between these different groups? So if you look here, there's much less signal, means that polymer chains on now NOMS, these tethered polymers, are a lot more stretched out and then far away from each other. We somehow or another created a lot more free volume, as shown here. There's a lot of free volume. We can really jam pack CO2 along the polymer chain, also have a better accessibility of functional groups along the polymer chain. So we tested our hypothesis. We started to graft more amine functional groups, as shown here. The red colors is the nitrogen groups, where CO2 can really interact with these amine groups. And as we expected more amine groups, we were able to get a lot higher CO2 capture capacity as expected. So all these signs are great, but we were still making very small amount of NOMS in our labs. So next thing was, we wanted to make a much bigger batch and then create a reactor system to do this. Then we had to start thinking about, how are we going to move all these liquids around? And this is the figure of data on viscosity. So if you look here, this is function of temperature, and the bottom data set is an MEA solution, monoethanol amine solution at 38%, which is one of the state-of-art CO2 capture materials. Second group right here with the red dots and cross dots, circles, these are the ionic liquids. In the top, these data sets are our materials. Obviously, our materials are a lot higher viscosity. It's really viscous like honey compared to MEA solvent, which is very easy to design, very easy to pump, very easy to create gas-liquid interfaces. Another sad point was here is that it's not even a linear plot, it's a log plot. So as soon as we saw this, and we were like, this is really challenging. What are we going to do? Because at this viscosity, there's no way we're going to use same reactor as a CO2 capture reactor used for MEA solution to do the CO2 capture. Our colleagues doing ionic liquid, they were very brave. They said, oh, we can tune or reduce this viscosity. But we were looking at our viscosity. It's tens thousands of viscosity. This was way too high for us to do anything. So what we decided to do was, what is the biggest problem with the viscosity? Majorly two. First, mass transfer will be really challenged, right? And same as a heat transfer. At the same time, moving these materials around between different reactors will be very challenged. So we decided maybe this will be a good opportunity. So there are a lot of research going on, including my group, looking at hydrogen bonding change, equilibrium shifting. But let me tell you about encapsulation today. If you have really sticky and highly viscous material, and if we want to create a lot of interfacial area, maybe we can chop them apart and keep them apart by packaging them. So we start looking at the encapsulation technologies with Lawrence Livermore National Lab. We created this microfluidic device. Now we are using a somewhat different system, but initially this is what we decided. So what we did was, within this microfluidic device, the blue fluid is NOMS material, captures CO2, and the white color fluid is a UV curable polymer. And then there's like a third fluid just pinching off these micro droplets. Once we make droplet inside a droplet, we just had to UV cure downstream. And because our NOMS material was not bothered by UV at all, that only thing happened was the shell material was solidified. And the key was this UV curable shell material was gas permeable. So now you have kind of inverse membrane. The membrane kind of capsuled the liquid, which has zero vapor pressure, which means that this liquid sag, you can leave it outside for days and months and years. There will be no evaporation of this liquid which is inside. So these are some of the materials we actually made. You can make these in the single core like here, or multi-core, and you can change the overall size and thickness of the size and all that. If you do that, so compared to neat gnomes, this is a neat gnomes, it was very, very slow to capture CO2. But as soon as we encapsulate them, we were able to increase the kinetics, so that now it is possible for us to use this to do CO2 capture. So let's talk about the point source versus direct air capture and direct ocean capture CO2. Until now, I was telling you the materials, and all these materials so far, maybe up to 5 years ago, we were focusing on power plants. Or the guideline was, can you capture over 95% CO2 from flue gas of the any power plant, including the waste to energy plants? I don't think waste to energy plant, none of the power plants are regulated yet, but always target was power plants, burning fossil fuels. But nowadays, about 5 years ago, we started thinking that, well, we are maybe too late. Not only point source capture, which is going from positive emission to zero emission is important, but maybe we should even go back into the history and picking up the CO2. And that means we need to start doing negative emission technologies. One negative emission technologies, there are many of them, many scopes of these available, is that whatever carbon you captured has to come from the environment. Environments, there are three, right? Gas, liquid, solid in terms of environment. So gas is sky, the liquid will be ocean, and solid will be rock. So usually limestone has a lot of carbon in it. Don't touch this. So normally what we are looking at either CO2 from sky or CO2 from ocean. If we are capturing those, and then if we can put it away and store it, then we can say it was a negative emission technologies. You can go through a biological route. So if a biomass has been grown by capturing CO2 from air, and if we burn it or even just bury it or convert to biochar and bury it, all these can be counted as negative emission technology. We can do something similar. We call it coastal blue carbon, or the seaweeds or biomass around, near, or inside the sea can be captured and stored or converted. Energy can be even extracted. All these can be negative emission technologies. This report has been published by National Academies in 2019, and I think it's a great read for you to read. But usually biomass is growing somewhat slower. So that's why people start looking at direct air capture, doing it chemically, or direct even ocean capture, chemically capturing CO2 from environment. I think, in my opinion, that it shouldn't be point source versus DEC or DOC. It should be both, because we are already too late. The challenge is a little different, especially direct air capture. If you look here, direct air capture is dealing with much lower concentration, because power plant CO2 concentration is as low as 5 if you have natural gas firing power plant. It could be as high as 15 if you are burning coal. But you're starting with only 400 ppm, which is very, very low in air. Because of that, we're not trying to capture over 95% of CO2 from ambient air, because it would be almost impossible. It would take way too much energy. So over 60%, already great. There are other challenges for direct air capture compared to point source capture. You need very low pressure drop, because moving so much air to capture same amount of CO2, it makes it really difficult to compress all that air. So you cannot have a high pressure drop across your reactor as shown here. This is much lower pressure drop across the bed. And you need to have a material which is very stable under high oxygen concentration, because in air, we have 21% oxygen compared to in flue gas, we have very little amount of oxygen. And if you have a lot of oxygen at high temperature, it can really degrade a lot of materials a lot faster. And also this direct air capture unit is sitting outside so that you have to deal with all these incoming temperature, pressure, other pollutants, and humidity, all these environmental conditions you have to deal with at the same time. So a lot of research is happening in the United States, especially the last 3 years. There's a lot of government funding as well as industrial funding going into this area. And in terms of materials, I'm very interested because what I just showed you, this now encapsulated this liquid because it doesn't evaporate. Now it's became big chunky particle. You're kind of combining the benefit of liquid solvents as well as solid sorbent in one. So we are applying this for direct air capture right now. The encapsulation technology can also encapsulate these nanocrystals like a metal organic frameworks. I think there's a lot of versatility in a sense that not only you need to think about what materials can really do good gas separation like CO2 capture, but also how you're going to deliver these materials depending on where you're trying to capture CO2 or other gases. I think there's a lot of innovation we still have to go through. But next question is, so what? What are we going to do now we capture CO2? That's a big question because you're not going to do catch and release and done with. You're not going to release back into the atmosphere because that doesn't make sense. We need to do something. And if you do care about climate change, as we listen to that little video, you have to store. At the end of the day, you really need to store a large amount of CO2 because we're emitting way too much CO2 into the atmosphere that we cannot utilize all the CO2 we emit. So until we decarbonize many of the industrial sectors, if you care about climate change, you have to store. Today, I'm not going to tell you much about the storage itself, but there's many different reservoirs we can actually inject CO2 and safely store CO2 in there. But one area I'm interested in is utilization. So what I want you to do is look around your room right now. Can you tell me there's any item does not have any carbon in it? I think it would be very hard for you to find any material around you does not have carbon in it. Because carbon is essential. When we complain about the carbon dioxide, we should not complain about the molecule itself, because without carbon, hydrogen, oxygen, we cannot have, our cells not going to be here, and we cannot have any of the materials shown in these pictures. So we cannot decarbonize materials and chemicals, because without carbon, these don't exist. But what we can do is defossilize these chemicals and fuels and materials. Because as long as the carbon in these materials and chemicals are not from fossil carbon, why not? So then this question becomes very interesting. So then the first question is, can we build our new economy based on non-fossil carbon and hydrogen and oxygen and all that so on? So I think hydrogen, you kind of know, right? Because we can split the water and make hydrogen. But carbon, where are we going to get the carbon? Going back to the negative emission technologies, we have 3 options. And the question is, what are we willing to use? Because once you start to harvest, some people even call themselves air miner, because you're mining carbon out of the air. I think this becomes kind of interesting because we hate sometimes, or a lot of environmentalists say mining is the worst thing we did on Earth. But at the same time, now you're grabbing elements out of the different environmental parts, sectors like sky and ocean. Now you're changing their chemistry and physics and so many other things so that you will have impacts. But what kind of impacts? So there was this is another plot from Department of Energy. They said that once we capture CO2, we can make all kinds of things, which I agree with them. We do know how to make them. But the question is kind of interesting because they started with capture CO2 in the center. Because of what they said was, once we capture CO2, and that captured CO2 is usually given to you as a pure CO2, dehydrated, and 150 atmospheric pressure, which is required for the pipeline. But then if I'm going to combine capture CO2 or CO2 capture with conversion, do we really need that? That's one of the first questions. If we say, instead of saying CO2 is a waste, we're going to start calling it a new chemical feedstock, then does it really need to be pure 150 atmospheric pressure and no water attached to it? Maybe, maybe not, depending on what you're trying to make. Another question is, there are many things here, right? Or these little bubbles, carbonates, liquid fuels, fertilizers, or even fire extinguishers, yeah, they can be made using CO2, but their market size is quite different. So what is the one will make a biggest change in our market in terms of lowering carbon footprint? So this is one of the latest report I saw from McKinsey, which was published in 2020, which is just last year. I thought it was very interesting. And interestingly, they're talking about 2030. So this is a technical potential of carbon capture, utilization, and storage in 2030 in their projection. The light gray one is a storage potential. I hope this is underestimated. Hopefully this bubble is as big as possible because this will be great for our climate change mitigation. But they also have the black bubbles, which is the CO2 utilization and conversion. So for example, there's a construction materials. This is a really big bubble, in fact, and our built environment has a lot of carbon in it. So one pathway is a mineralization. Carbon can be mineralized to make solid carbonates. And that's nice because now CO2 is going downhill in terms of thermodynamics so that you have thermodynamically stable carbonates and solids. So unless you burn these carbonates, you're not going to release back carbon dioxide, which is great. So if you look here, this is what kind of feedstocks are available for carbon mineralization. The red bars are the natural materials like seawater, silicate minerals, and all that so on. But we also have these materials, which is industrial waste. Unique thing about these is that fly ash is from power plant, steel slag is from steel manufacturing plants. All these industries are also point sources of carbon dioxide. So they actually make acidic gas, carbon dioxide, and solid waste, which is base. So that by reacting those two, you can actually decarbonize themselves. Of course, they don't make enough steel slag to fully decarbonize the steel manufacturing plant, but every little bit helps. And this is the log plot. And now people are starting to, including my group, looking at construction materials and demolition materials, how to use those to capture and store CO2 and even utilize. So one of the example technology is we actually have a startup company on this. So this is a steel manufacturing, which is conventional way. Conventional way of making iron and steel creates a lot of flue gas and waste heat and solid waste, which we just had to deal with. But our new technology shown on the right-hand side, we actually combine those as a CO2 as a carbon feedstock, slag as a alkalinity feedstock, and then waste heat to use that energy to do the carbonation. So through this technology, we are working with a Chinese steel plant in Baotou. We make paper fillers and plastic fillers and iron oxide, and we are even recovering critical elements out of these waste streams. And it has been really wonderful because we minimize the landfill of the solid waste as well. Another technology we work with steel slag is that by using steel slag, we actually tie into biomass conversion like a wet and salty seaweed and food waste into biohydrogen. And this particular reaction called alkaline thermal treatment of biomass is very unique because you're reacting biomass, which is some mixture of carbon, hydrogen, and oxygen with a strong base like NaOH. Then what happens is that all the carbon in biomass or seaweed or food waste trickle down to lowest energy level of carbonates. At the same time, all the energy are pushed upwards as a biohydrogen. So only thing you left is a solids with only gases product is hydrogen in single step reaction at ambient pressure and about 250 to 300 degrees C. So by doing so, we put all the carbon into solids, and we can even reapply this into the field to remineralize the field, increase the food production much better. So let's go back to this McKinsey plot, because the biggest one is fuel. And there's some little ones, but also plastics and chemicals as well. So all these things by 2030 can be utilized by non-fossil carbon and taking up this market, according to McKinsey. So what limited us? Because we knew how to do that even long along. But the challenge was, in order to do CO2 conversion to chemicals and fuels and plastics and polymers, we needed carbon-free energy. Doing that with the energy which emits CO2 doesn't make sense when you do life cycle analysis. But good thing is, now we do. Our renewable energy, electricity, for example, is going down in its price in the United States so rapidly because we install this renewable energy a lot faster, solar and wind. At the same time, we don't have really good storage mechanism yet. So then because of that, sometimes we have even negative price of electricity in California. So once now we have carbon-free energy, we need to have good catalyst to put carbon and hydrogen in a way that we can make high-value materials. But we don't talk about the hydrogen, right? Because when you try to make chemicals and fuels, not only you need carbon dioxide, which is carbon in it, but you need also hydrogen because all the materials has both carbon and hydrogen. But unfortunately, carbon dioxide has only carbon and oxygen. So the question becomes, where does this magic hydrogen come from? And a lot of times people just talk about hydrogen comes from by splitting water. But it's not as simple as that. So right now in the United States, we're talking about 4 different colors of hydrogen: black, gray, blue, green. And obviously, I think most people like blue and green, right? So there are many different options. And that tells you that you really need to understand where all the components came from to make sure that what you made was really sustainable materials. So let's look at this hydrogen economy in a sense. This is from National Renewable Energy Lab in the United States, came up with the hydrogen at scale concept. They were looking at how to link hydrogen economy to electrical grid. Without going into that, but they had a little bit of CO2 here and there. And now what we have to do is link this entirely to carbon cycle. And by integrating them together, we can truly decarbonize or defossilize our not only power sector, but also chemicals and materials sector, which is very important if we really want to achieve climate change mitigation. So last little bit, I want to tell you a little bit about combined CO2 capture and conversion. So if you look at the overall scheme of it, what we are trying to do now in academia and working with industry globally is that not only focusing on power plant for CO2 capture, you need to look at a wide range of CO2 sources, including point sources like the chemical industry, cement manufacturing, steel manufacturing. We are going as far as ambient air as well. But once you capture CO2, can we deliver that CO2 to the catalyst, effectively convert this to high-value materials? Only feed of energy will be renewable energy. And some we can just go back directly and recycle, but maybe some of them will be emitted to the air, and then we have to recycle back into the complete cycle. If we can do that, we can say we defossilized our chemical and materials industry. So we kind of look at, okay, in order to host that reaction, I went back to our material called LUMS, right? Can we do that? Can we capture and convert CO2 in the single reactor? Wouldn't it be great? So the left-hand side is a NOMS in secondary fluid, for example, water. On the right-hand side is the exactly same polymer, but untethered in the water. When you look at these two together, we're thinking about if I want to do electrochemical reduction of CO2 to make high-value materials, which one will be having a higher conductivity? I totally thought the one on the right with the polymers will be the one. So we did the test, and it was really interesting because this is the untethered polymer. This is our NOMS. In a really weird way, at the concentration range we studied, the viscosity of NOMS-based secondary with the mixed in water had a lower viscosity and higher conductivity, which is great news, but I did not understand why. So we really start digging into this, and then what we realized was maybe the system wasn't looking like this. Maybe system was hierarchical structure within the system so that transport behavior within the system was a lot different than what we thought. So we took this to synchrotron at Argonne National Lab, and normally if you look at the nanofluids like ours, you should have only signals at high Q range, because the length scale is very, very small. But then when we looked at it, there was a lot of signal at the low Q range. which means that it's the inverse of the length scale, so that there's bigger structures within the system. So now going back to putting everything back based on our synchrotron study, now we see that this really homogeneous looking material is in fact agglomerates of micron scale and aggregates in the nanometer scale. And because of that, transport behavior was very different. And in fact, it was enhanced. So we were able to even capture CO2 at a much faster rate than we thought. So this is the example of what data looks like. This is the without salt, and this is with salt, because you need salt when you try to do electrochemical conversion. This is without our NOMS material. If you look at regular electrochemical reactors, in the regular electrolyte with just potassium bicarbonate. But then as we increase the NOM concentration, you can really pack CO2 into this system a lot more. And even more, what we found out was in our system, not only the NOMS material in bulk becomes kind of internal reservoir for CO2 and release the CO2, and CO2 gets absorbed to the surface of the catalyst and get converted to the product, but it also hovers around and then kind of interact with the CO2 during its conversion, as shown on the right. So then now we can even call NOMS, maybe it's behaving like a co-catalyst. So then either way is really interesting, and we confirmed this by looking at the Faraday efficiency of different products, and definitely it changes by adding these materials. This data shows you that by adding NOMS material, you can have a lot higher, you can actually combine CO2 capture with conversion in a single reactor, but also you can target and tune for the product you really want. So the overall picture is this. What we are really looking at is complete the cycle of carbon and hydrogen, and we can even capture CO2 from ambient air using carbon capture, electrocatalysis, and biocatalyst. We can really make a platform molecules throughout the system. And only energy input will be renewable energy. But challenge becomes what we don't know, we do not know, and we are trying to work on is or at the interface, where CO2 is coming in, local CO2 modeling, how to hand off CO2 from the electrolyte to electrocatalysis, from the electrocatalysis to the biocatalyst. I think there's a lot of interesting studies we need to do. So, but we have to go back to the question why we did start or this journey of doing this study. So let me ask you, which one is better for the environment? Jet fuel from crude oil or jet fuel? I just told you I can make it from capture CO2 from air, hydrogen split from water, and renewable energy. Let me give you an easier question. Paper cup versus plastic cup. We can have this discussion, but at the end, I like to say we need to consider all the CO2 sources, and we need really multifaceted solutions for CCUS. CO2 utilization will play an important role, an interesting role to defossilize our industrial sectors. And reactive separation, systems engineering, process intensification, all these are critical pieces for our overall sustainability. And we really need to consider new pathways to existing chemicals, but even more, new pathways to new chemicals. Should we really have same commodity chemicals for the future if we think of CO2 as our chemical feedstock? And more importantly, technologies should be developed considering the environment, our environment within the system boundary, not outside. I would like to thank all my students and collaborators and funding agencies, and I'll be happy to answer any questions. Thank you.
Thank you, Professor Park, for your comprehensive and interesting presentation. So now we can start the Q&A session. So the attendees, if you have any question, you can send your questions via chat function. If not, you may raise your hand, and so we will allow you to talk with the speaker directly. To start with, I would like to invite Professor Xianang Wen to initiate the discussion and moderate the discussion session.
Thank you. Thank you, Park, for the always very inspiring talk, and we really learned a lot through your lecture, and a lot of different aspects for the sustainable and low carbon development. I have already received many questions from the chat channel, so let me read those questions first. Let me check if the audience is here. You can actually unmute yourself and ask the question, right? So first question is from Mr. Kyung-wook Hwang from Ojung Eco-Resilience Institute at Korea University. Actually, I think you are here, right? The question is about each country's different environment where carbon dioxide can be captured and stored. What are the conditions under which carbon dioxide can be stored reliably for a long time?
In terms of only storage, the question is only on the storage?
Yeah, storage is...
okay, so capture is different. If you're capturing CO2 from point sources, it will be similar because most of the power plants are operating very similar manner. But if you're talking about CO2 capture from air or ocean, it would be very different because the temperature difference and humidity difference and CO2 concentration is somewhat similar everywhere, but then everything else is changing. So it will be a big challenge, but something we should address anyway. So a lot of direct air capture, direct ocean capture researchers are looking at is all that fluctuation of the environment and how that impacts their operation. In terms of storage, that's a little bit of sad story for Korea because we don't have good storage sites. You really need to have a large reservoir in geological formations, either on land or under the sea. And Korea doesn't have one. And another thing is by injecting 150 atmospheric pressure CO2, you will definitely create earthquakes. The question is it going to be such a baby one so that you don't feel it? Or is it going to be huge episode? That's very important because whenever you inject any high pressure fluid, you will definitely disturb the energy field so that you will create earthquake. But most of the earthquakes, you don't feel it. So you want it to be dissipated slowly, not with a huge episode. So that you have to do a lot of good survey in the storage site, whether there will be any issue with the earthquakes, or is there enough of permeability, which is connected pores so that you can fill all those pores? All these are very important questions. I think in the United States, we have quite a bit. Europe, quite a bit in offshore, but offshores are more expensive. But overall in the world, we have plenty of storage sites and enough storage capacity. But all these injected CO2, they're stored as more likely either liquid or supercritical CO2, which means that these are fluids. So it moves around. So not only you have to inject, you have to make sure that you have a monitoring wells and monitoring devices so that you know where they are going because they will migrate to high to low pressure. So most permanent way of storing CO2 is making rocks. If you can make a mineralization, make a solid rock like a limestone, it won't go anywhere. Unless you burn it, it's not going to release CO2. But all those things takes energy. So if you're talking about the cost today, easiest thing to do in the large volume is injection into geological formations. If you want to do no monitoring, you just want it to be geological time frame, just stay safely, you have to turn it into rocks.
Thank you. Thank you for your answer.
No problem.
All right, so next question is from Dr. Liang Shi from Nanjing Agricultural University. So it's very interesting. Dr. Shi is asking, what's the effect of COVID-19 on carbon capture, utilization, and storage?
That's really interesting question. So there was I think even air pollution has changed, right? Because the people stopped traveling, so or the emission came down. So I think that was really interesting. But remember one of the picture I showed, the Petronova project? So it's not about whether it's good for the environment or not. Petronova project shut down on hold now because crude oil price went down because people stopped traveling. Because the way they were making sure that they are economical is they capture CO2 and sell that CO2 to enhanced oil recovery site. So that the enhanced oil recovery site was saying that, oh, we can't get enough money for the crude oil we just recovered, so we don't want to do it. Since there's no CO2 market, they stopped doing CO2 capture. I'm not saying COVID was bad for CO2 capture. No. It's a good thing. But I think less traveling, people being more environmental, CO2 issue and environmental issue are really tied to each other. So less resources we use is better for the environment for sure. So I think COVID did quite a good things for the environmental, not for human side, but environmental side of it. But long term, we'll recover from this. And then eventually we have to do carbon capture.
Awesome. I think we read some, investigate some data to see now the COVID has seen a V-shaped recovery already. The previous down of the CO2 emissions now has been fully recovered. So
I know.
The
we're too resilient. Yeah.
Hopefully the environment. I think the global collaboration is getting more and more close and solving those issues in future.
I agree.
Thank you. So I think the audience raised some questions, right? I see someone is raising hand. If you want to ask questions, please raise your hand again in the virtual environment so we can call your name. Let's continue to see the questions received. So, all right. So Ms. Yura Ko from the Audrey Institute, again from Korea University, asked, would the CCUS technology for blue hydrogen production be a stepping stone towards the optimal green hydrogen level for energy sustainability, or could it also be a level of ideal energy production level by itself? So
I don't think I got the question. It's
about
about hydrogen, right?
Yes.
Can you repeat the question again?
If you're here, maybe you can ask the question yourself. You can unmute yourself and ask. I think the question is about the combined CCUS with hydrogen production, right?
Oh, got it. So hydrogen is very important because most of the time when people talk about CO2 to chemicals and fuels, they just put arrow and then hydrogen. But where is that hydrogen coming from? Because hydrogen the cheapest hydrogen is still from coal. So you can gasify coal and then make a water gas shift reaction and get the hydrogen. That's the cheapest hydrogen in the world right now. The second cheapest is from natural gas. In the United States, natural gas is the cheapest one because we have shale gas. But in the rest of the world, more likely coal is the cheapest and then natural gas. So black hydrogen is from coal, gray hydrogen is from natural gas, and green hydrogen is by splitting water, which is the best one. And blue is as good as green. That's what they claim. I don't think so, but that's a steam methane reforming with carbon capture and storage, which means that you make it from natural gas, but we are capturing CO2 and storing it. So they're claiming that there's no carbon emission. We still have to do a full life cycle analysis, whether that's true, but I think it's getting close to it. So both blue and green hydrogen is good. But one of the challenges, if you look at the economics of the electrolyzers making hydrogen right now, splitting water, is very good. You can buy off the shelf the electrolyzer at really low cost, and you can make hydrogen quite cheap. The problem is the electricity going into that electrolyzer, where is that electricity coming from? Was it burning coal, or was it burning natural gas or waste or renewable energy? That's important. So assuming that renewable energy is still not economical. Not only that, the problem with the renewable electricity is if you have renewable electricity, you should use it as electricity first. And whenever there's no need for electricity, then you can do something else. So that there's something called capacity factor. So electrolyzer is cheap today or affordable today, assuming that your capacity factor is 1, which means that you're running it all the time, 24/7, 365 days, then it's economical. But if your capacity factor becomes like 0.2, 20% of time, now your electrolyzer cost has to go down by 1/5. So there's a challenges with the capacity factor. So I think in order for us to defossilize, not only we need to lower the cost and develop the technology for carbon capture, but you also need to figure out how to make hydrogen very cheap with the fluctuating renewable energy supply. And that's very important for the future.
Indeed. Right. So any question from the current audience? If not, I will continue.
I have one question.
Okay, sure. Please go ahead.
First, thank you very much for your great talk, Professor Park. I remember, as you mentioned in your slide 4, one finger is talking about the carbon capture technology made by the National Energy Technology Laboratory in 2010.
Yeah.
So it is about 10 years ago. So among all the CO2 capture, current CO2 capture technology, which one could be the most viable route to achieve the carbon neutrality from your perspective?
Yeah, so although it's the 2010, I couldn't find later one. I think there's no years on the x-axis, right? They keep using the same one because everything is shifting left-hand side without changing the years. Because on the x-axis, they did not have exact years in 2010 or whatever. So what they're saying, I think if you're talking about power plant CO2 capture, right? We've been developing all these CO2 capture materials, either membrane or liquid solvent or solid sorbent, for about 12 to 15 volume percent CO2. So we already knew what binding energy has to be to capture CO2 over 95% with the decent amount of rate and all that. Now, problem became challenging because now we are burning natural gas in the United States because all the shale gas. Now our flue gas concentration is only 5 to 7%. So all the materials we developed for power plant CO2 capture when we are burning coal does not work as well. So now we have to redesign the materials a little bit. So we have two options: either accumulate the CO2 within the system, boost it up to 15 or 12, or we have to have new materials. But having said that, the Petronova material is still liquid solvent. So liquid solvent with the different types of amine is the best one so far because it's so much easier to design the reactor and heat and mass transfer much easier, and creating all the interfaces with the packing material. We're trying to develop the better 3D printed packing material and things like that in the United States. That's that. Whether we can use that same technology for direct air capture, no. Because the direct air capture, you don't usually have that kind of system, so that you need to have, most of the time, except one company, they're all looking at solid sorbent. Because if you do liquid solvent, let's say you have very dry day in Arizona, and then your air came in and you have 38% MEA solution in the system, you can capture CO2 really well, but also you lose so much water because you're humidifying all that air as well, right? So there's a lot of challenges if you're trying to do direct air capture. Membrane and solid sorbent in the United States, the latest data show that they have challenge with the water. Any material, which is solid or membrane, dealing with the CO2 capture, they also love water. So the competition between water molecule and CO2 always a big challenge. So either you have to dehumidify the flue gas stream, or you have to deal with the water. So I think if I have to build something today, I will do liquid solvent.
Yeah. Thank you.
No problem.
Thank you.
So we received a very interesting question from Paul Park. I think Paul is in the audience as well. He's asking about either we can injecting the CO2 into a space, right? You can ask a question yourself.
Yeah. So sorry for disturbing Alicia and Shannon. Actually, Paul is our undergraduate student. He's the freshman, so he just graduated high school. So look like his question looks quite interesting. So please go ahead.
I think we need a young generation to get more thoughts.
Right.
Yeah. First of all, thank you so much for an amazing lecture, Professor. The question I'd like to ask is regarding the disposal of the carbon captured products, like Professor Wang has told you before. I would like to ask, instead of storing the products on Earth, since it can disrupt the environment, what do you think about ejecting these products into the outer space? I know it's very costly at the moment, but as time progresses, I think it could be a better option instead of storing in the Earth. Thank you so much.
No problem. I think, brilliant student. I'm very impressed. We were even talking about this when I was in undergrad, I think. That's been a while. But I think we used to dream about, me and my friends were talking about, oh, maybe we should have a long pipe going all the way to the space and then continue to feed in some gases we don't want and then send it to the space. We can definitely do that. But what I was told, and I kind of start to learn more about it, is that there's a lot of waste in space now. which will be a big problem for us to deal with. If it is gas, maybe it's okay because it will diffuse into this vacuum of things. But I think a solid waste, if we convert into solid, this will create another problem. I think that's a problem with any of the waste management. If you're moving from one place to the other, you're just moving the problem from one place to the other. So I think that's a challenge. If we bury it, at least we know where it is. Space, if we put it there, if it's gonna be only one dump site, maybe it will work, right? But if it's gonna be diffused and we have to collect them back in the future, there'll be another challenge, I think. But kind of interesting question, yeah.
Thank you very much.
Thank you very much for asking question. Actually, he's attending my class and look like he's very much creative. So, Alicia, actually, I'm personally pretty much interested in looking at field scale carbon capture and storage technology. How does each technology affect the biodiversity? So I think that's really challenging issue because the biodiversity is one of the key factor. So that looks quite complicated. Probably I want to share a slide at the end just for 1 minute and want to address some big question to all of you. Before that, my postdoc supervisor joined this webinar. I'd be surprised. He's from Canada at U of Alberta. So,
oh really?
I should invite Professor Scott Chang. Yeah. Hello, Scott. Good to see you.
Hi, Yoon-sik. Yes.
Yeah. Hi, nice to meet you.
Yeah, Professor Park. I guess I did my PhD at UBC.
You're kidding? Oh.
Yeah.
Alma mater for both of us.
Yeah, you did your, but you didn't do your
I did
PhD.
Undergrad there.
Yeah, you did your undergrad. I guess I was there between 91 and 96.
Oh my gosh, we did overlap.
Oh,
I started at UBC in 1995 as a freshman.
Okay. Yeah, I kind of left in the fall 95, moved to Victoria for 6 months, then to New Zealand.
Nice.
Well, that was a good question. The last question was interesting. I had a question for you as well.
Yes.
Kind of related to the first question that was asked. My question is, if you inject these liquid into the geological storage space, what is the risk for them to be escaping from the geological storage? And I guess it's kind of a second question for that is you talk about potential for causing earthquake and so forth. But I guess these geological storage space used to have compressed gas or liquid there to begin with. And we didn't have earthquake before. Why injecting this complex, high pressure liquid into this geological space would cause earthquake?
Good questions. So there are different types of geological formations. So if you're talking about depleted oil well, you're right. Because usually oil wells have a head pressure. So when you take the crude oil out, it usually comes out with the pressure and depressurized. Once you take all the oil out, like enhanced oil recovery, then you can store it, no problem. A lot of CO2 injection in the United States and rest of the world is happening in aquifers. Aquifers is not storage for high pressure gas. So usually it's not under high pressure. It's just a hydrostatic head. That's it, right? So that if you put CO2 in it, water is not really compressible. So what happens is as you put the CO2 into high pressure CO2 into this, although supercritical CO2 can dissolve into water phase, it's a very minimum because you have big blob of CO2 coming in so that all the brine in that groundwater area get pushed outwards. So unfortunately, they get displaced. So what are the environmental concerns? I think in terms of leaking, not as much, just because it is really, you need to find the site very carefully so that there's a really good cap rock. so that there's a thick cap rock so that it's below that, so that CO2 cannot migrate up. You cannot even crack the cap rock. That's where you need to store. Where the leakage really happens is where we puncture the earth, injection sites. So all the injection sites and monitoring sites, there's a lot of leakage. It's similar to methane when you try to get the gas out. So those are the areas you need to really well use as good cement. And cement also degrades over the years. So if you don't maintain it, you will definitely have a leakage. In terms of aquifers, because you just have filled with water, you're putting a lot of gas into it, you will build up the pressure. So if it is depressurize itself by migrating to other areas with more porosity, it will be okay. But if it doesn't happen, it can create earthquake. But we haven't had any big episode yet, but you hear about, I think a number of years, almost 10 years ago, there are huge mega dams in China create an earthquake, right? It's a similar concept. Basically, you're putting a lot of pressure in one point so that it had to release that pressure. So how you do injection is also important, right? Because if it builds up too much pressure, stop, right? So that you just need to operate it so such a way that it doesn't have a huge earthquake, hopefully. And the important thing is you need to also do, there's something called MVA, is monitoring, verification, and accounting. Because monitoring is very important for the future, right? Because we want to make sure where it's going because it's still mobile, right? Second thing is verification and accounting, because people can claim that, oh, this CO2 here is my CO2, I injected, give me the credit. But it may or may not, right? Because we don't, unless you tag every CO2, it goes and mixes with other CO2. So it's really hard to say whose CO2 just leaked. So there's a lot of legal issues as well. Yeah.
Great, thank you.
No problem. Thank you.
Hey, so
we have time for a last question, or we have passed the time a bit, but last question is from our APRU officer, Tina Lin. Actually, if Tina wants to ask a question yourself, it's in the chat window. It's about the CCS technologies. How long do you think it will be affordable for most of the countries?
So carbon storage only, I think it's still it is already affordable. It's not very expensive technology. Storage injection and storage is not very expensive. The expensive part is the monitoring and verification and accounting. Because if you're trying to do monitoring, it's a maintenance. Like you're doing it every day, right? Until rest of the lifetime of the reservoir. So unless monitoring technology is really cheap, you will really cost you for over the duration of carbon storage. Carbon capture right now is of about $40 to $60 per ton. That's not too bad. We can actually do it in the point source. Direct air capture and direct ocean capture is a lot more expensive, right? Because you're starting with the much lower concentrations. But in different countries, more renewable you have in your country in energy mix, you'll have a better chance. If you're still burning a lot more coal, you will have a lot harder time. So I think that the key for achieving carbon capture and storage is interestingly, uniquely tied to how decarbonized our energy sector was. Yeah.
Right, perfect. We really had great experience listening from Professor Park's insights. So I think we have cleared most questions. If you have further questions, you can read them later in the chat window. And we will
you are welcome to send me an email.
I think we let Tina Lin in. She has a question.
That one was just answered about the cost affordability.
Right. So,
that's already.
So Tina, are you there? Actually, Tina is working at APRU headquarters. So just probably she can say hello to all of us. Maybe not.
She will not be able to talk.
Okay.
She's here.
So she's here, right?
Okay.
Yes. Tina, can you hear us?
Just said she can hear, but I guess maybe her microphone is not working.
Okay. So again, thank you, Shannon, and thank you, Alicia, for your great talk and your moderating the overall speech. So before we finish this webinar, I'd like to share one very important aspect on climate change effect on biodiversity. So please let me share a screen with you all. Can you see my slide?
Yes.
Yeah. So next May 18, APRU Sustainable Waste Management Program actually hosts, together with our Ministry of Environment and our President, the People's Presidential Meeting. As you know, the 12 presidents are involved in this People's, and they're going to be held end of May. And we organize Nature Forum, named the People's Nature Forum, Climate Change and Biodiversity. That's on May 18, and that's fully sponsored by President Bae Yeon-jae at National Institute of Biological Resource at the Ministry of Environment, together with 2021 People's Summit Seoul. So this is supposed to be held in Seoul with all the presidents in person, but eventually it's gonna be held virtually. And we are able to invite Professor Gretchen Daly from Stanford University and Kate Jones from UCL, and we have really wonderful speaker. They're going to talk about some of the questions that we had today, kind of climate change effect on biodiversity and business, especially the environmental pillar, environmental social governance, focusing on natural capital and biodiversity monitoring and its relation with climate change. Finally, biodiversity and COVID-19. So we have editors gonna chair this session together from Nature Climate Change, Nature Review Earth and Environment, Dr. Laura Jinke, and Nature Ecology and Evolution, Nature Communication. So again, the event is 100% free to all of you, and it's real time. So I really hope to join this important event and have a extensive discussion for climate change issue as well as biodiversity. And yeah, and I put a link to the event in the chat menu. So and it was great to see you all, and it was really great to Scott. And I lived in Canada in 2004 and 5, and sorry, the 6 and 7 and 13, 14. So anyway, Kumu, can you give your concluding remarks, and we finish for webinar for today.
Thank you, everyone. So this is the end of second session of Global Lecture Series. So I would like to extend my sincere gratitudes and appreciation to Professor Park for your valuable contribution and for sharing your knowledge with us during your busy schedule. I also extend my special thanks to Professor Shannon Wang for joining as a panelist for this event, and also for Professor Scott Chang for joining the discussion session. Thank you very much, Professor Ock, for organizing this event. Last but not least, thank you all the program leaders and all the participants for supporting and attending this event and bringing your expertise to this gathering. Thank you very much. So have a great day.
Thank you, and hope to see you soon in person. Thank you very much. Bye-bye.
Bye-bye.
Thank you.
Thank you.